Okay, welcome to the second video in my series on the t-distribution. In this video, we're going to be deriving the t-distribution. So let's go ahead and jump into this. Okay, so we start by noting the fact that we've got a random variable x that comes from a normal distribution, and that we go ahead and take some random samples from that distribution. So these are going to be our random samples from that distribution. And we're going to go ahead and define our sample mean to be, what you normally would expect. And then our sample standard deviation will also be the typical sample standard deviation formula. Like so. Okay, so from here, typically if we have a normal distribution and we happen to know the population standard deviation, then we can write down x bar minus mu divided by the population standard deviation, the quotient of the population standard deviation, and the square root of the sample size. So this is a typical way that we can do this because we know that this happens to follow a normal distribution. And not only that, it follows a standard normal distribution. But the problem that arises is that, oops, that's not what I wanted to do. The problem that arises is that oftentimes this population standard deviation is not known. And so the next logical thing is to use an estimate of that. So in other words, use the sample standard deviation. And so we get that t is equal to x bar minus mu divided by s, the quotient of the sample standard deviation and the square root of the sample size. Okay, so here's our, what we call our t statistic. And then from this, we will go ahead and derive the probability density function. Okay, so we start by simply multiplying this by 1 in the form of sigma over sigma. Okay, so now that we've done that, we're going to go ahead and swap out in the denominator. We're going to swap sigma with the sample standard deviation. And so now I have this expression. And next thing I'm going to do is note that this can be written as 1 over the reciprocal of that. So it's going to look like this. I'm going to get x bar minus mu divided by sigma divided by square root of n. And then I'm going to multiply that to 1 over s divided by sigma. Now, if you don't believe that this and this are equivalent, just do a little bit of algebra to convince yourself. Okay, now the next thing I want to do is I want to create that random variable that we saw in properties of samples drawn from normal populations. So here I've already got one expression that has a distribution that I know. Okay, and so now what I want to do is turn this also into an expression that has a distribution that I know. So I've got x bar minus mu divided by the quotient of population standard deviation and square root of n. And then I'm gonna do 3 things here. The first thing I'll do is square this. So I'm going to get 1 squared is 1, s squared is s squared, and then sigma squared is sigma. Now, because I squared it, I have to take the square root, otherwise I've changed the value. So I take the square root. Now I'm going to do one more thing, which is I'm going to multiply it by 1 in the form of n minus 1 divided by n minus 1. So now I've got n minus 1 here and n minus 1 here. Now, the reason I've done that is because what we talked about before, one of the properties of population or random samples drawn from normal populations is that this term here follows a chi-square distribution. And so now I've got these two random variables that will follow distributions that are known. So in other words, I'm going to let u equal this x bar minus mu over sigma, and I'm going to let v be equal to this term, n minus 1 s squared divided by sigma squared. And then what do we know about this? We know that u follows a standard normal. So u is a random variable that follows a standard normal distribution, and v is a random variable that follows a chi-squared distribution with n minus 1 degrees of freedom. Okay, so now what I've accomplished is that I've got my t statistic in terms of two random variables with known distributions. And before I go any further, I want to make a substitution here. I want to let n minus 1 equal p, just to make my the rest of my work easier. So then what do I have now? I've got t is equal to u multiplied to p divided by b to the 1/2 power. Okay, so now, let me just make sure I got that right. Yeah, that's right. Okay, so now I just need to get the probability density function. So what have I done so far? I have rewritten my t-score in terms of two random variables that have known distributions. In fact, let's go ahead and write that down. So because u follows a standard normal distribution, then the marginal density function for u is going to be 1 over the square root of 2 pi times e to the minus u squared over 2. And then for v follows the chi-squared distribution with n minus 1 degrees of freedom. We'll call it p because we want to make it easier. So then our PDF for v is going to look like this. We've got 1 over gamma of p over 2, and then times 2 to the p over 2, and then multiply that to v, p over 2 minus 1, and then e to the negative v over 2. Okay, so these are our, hold on, that's kind of like, I feel like I want to move that so that it's more easy for you to see. Sorry about that. And I'll just change the color here. So f of v equals 1 divided by gamma p over 2. Well, no, it's too big. Just a moment, I will fix this. Let's see, make it a little bit smaller. Okay, and I'm gonna move it this way. So PDF for v is equal to 1 divided by gamma of p over 2, and then 2 to the p divide 2 times v. Then we've got p over 2 minus 1 and e to the minus v over 2. Okay, so there's our gamma distribution probability density function, and here's our standard normal distribution probability density function. Now, the other property of samples drawn from normal populations is that, random samples rather, is that these two are independent. U and V are independent. Okay, so what it means is that I've got this T in terms of U and V now, and what I can do, I can write down the joint probability density function for U and V. Because they're independent, it's simply going to be their product. So in other words, I can get this, that f of u v is equal to 1 over the square root of 2 pi times e to the minus u squared. And now my gamma, my chi-squared distribution rather, p over 2, 2 to the p over 2, v to the p over 2 minus 1, and then e to the minus v over 2. Okay, so that's my joint probability density function. Now, of course, we need to note the bounds for u and v. So u is available between negative infinity and positive infinity, and v is only from 0 to infinity. Okay, so that's great. We've got our joint probability density function. And what we want to do now is make a transformation. Okay. And to make the transformation, so why do we want to make the transformation? We want to use the transformation to get the probability density function for t. Okay, so here's what I'm going to do. I'm going to use this formula here. So I'm going to say f of t. Oops, hold on a second. Wrote that down wrong. So I'm going to get the probability density function is equal to the integral from 0 to infinity of f of uv. But then I'm going to put it in terms of some other variables here. So it's going to be, I'm going to use t and w. So I'm going to say tw, h1 of tw, h2 of t, tw, and then times the Jacobian of this, and then I'll get dw here. Now, okay, so what I need to do, I need to define here, I'm going to make the transformation from uv to t and w. Okay, so it's going to look like this. So currently we have t equals u times p over v to the 1/2 power. And then what I want to do is write, so u equals t times v over p to the 1/2 power. And then what I also want to do is transform, I want to substitute v, so say v equals w. So eventually I'm going to get u equals t times w p 1/2, like this. Okay. And so now I can write down this guy again. So my probability density function will be equal to the integral 0 to infinity f of uv. And that's going to look like this. T times T of, rather, hold on a second, let me fix this. T, and then square root of this quotient, and then W is going to come in here, and then I'm going to put my Jacobi here, and then dW. Okay, so then now we're ready to go. All right. Also, one last thing I just mentioned, I just remembered I should probably mention to solidify why these are independent, just in case it's not clear. And they're independent because here, this U is a function of X bar, and this V is a function of S. Okay. So if you recall, that's why these two are independent, because samples drawn from normal populations have that X bar and S are independent. Okay, so just make that clear now before I go forward. Okay, so we're going to now, we're going to take the Jacobi, we're going to find the Jacobi rather. And so in my formula, what have I done? I said let H1 of TW, I said that is equal to, so let me go ahead and write this down. So I said H1 of TW equals T times the square root of W over P. And I said H2 of TW equals W. Now my Jacobi, I want to find the determinant of this matrix, which looks like this. I'm going to get the partial derivative of H1 with respect to T, partial derivative of H1 with respect to W, partial derivative of h2 with respect to t, and the partial derivative of h2 with respect to w, and then I'll take the determinant, which will be like this. So just your typical determinant formula here. And like this. And this one here, that should be h1, my bad. h1, oops, with respect to w. Okay, now, sorry, I forgot the equals. So what does that look like? Well, first of all, we need to find h1, partial derivative of h1 with respect to t. So here's h1. The derivative of this with respect to t is simply this term, which is a constant, right? With respect, when t is our variable, this is simply a constant. And then we're going to subtract from it the derivative of h2 with respect to t, which will be 0. Okay, so basically I don't need to do anything else because this one will be, well, it won't matter because we're multiplying it times 0. So the Jacobian is this. And so now I can write down this expression, and I'm going to get this from 0 to infinity is going to be, so f of uv. And then here I've got t quotient square root w, and then my Jacobian over here. And then integrate with respect to dw. Great. Okay, so here's the transformation. The Jacobian transformation is wp to the 1/2 power, w over p to the 1/2 power. And so our marginal PDF of t is given by this expression here. Okay, so now what do we do? Well, remember, this is just u and v. So here's u, here's v, here's my Jacobian. All right, so what I'm going to do is I'm going to write down the PDF with these variables. Okay, so it's going to look like this. I'm going to get 1 over, so hold on, I think I need to write a little small maybe. So I'm going to get 1 over, so I'm going to collect all the constants into the front, 1 over 2 pi. And then I'm going to collect the constants for chi-square, because remember, v follows the chi-square distribution. So I get this one, 2 to the p over 2. And now, get my integral here. And the inside of here, what's going to happen, I'm going to replace with these variables that I have. So I'm going to have e to the negative. It's going to look like this. Hold on, let me make sure I write this down right. I'll look at my notes, okay. So because I rewrote it a little differently. So here, I'm going to have this divided by 2. And then times w here in the exponent, so that w is in my exponent. And then here I've got e. Wait a minute, w is not in the exponent, sorry, I lied. Okay, so that one's good to go. And then my w is going to be like this. This is part of the gamma. All right, yeah. And then I'm going to get e to the minus w over 2. So again, we're just like replacing variables here. And actually, you know what? Let me, no, it'd probably be a good idea to write this again in a different color. Sorry if you're writing this down, you don't need to erase anything. You're good. Okay, so let me try that again. So I've got 1 over the square root of 2 pi times 1 over. So you will memorize this if you write it down enough, but in general, you don't need to memorize this kind of thing. Let me try that again. So gamma of p over 2, that's a p, and then 2 to the square root, 2 to the p square root, and then I'm going to multiply that That's my integral here. And I'm going to get, first of all, the E negative T squared WP over 2. Okay, so that's just the standard normal PDF, right, with these variables in here. And then I'm going to take my W here, and it's going to be P over 2 minus 1. And then I've got an E to the minus W over 2 instead of V, right? And then my Jacobian over here, W over P with 1/2 E W. Okay, now you can do a lot of algebra and simplify this to get the next expression I'm going to write down, which is going to be 1 over square root of 2 pi. Multiply that to, wow, that's a large 1. So I'm going to take this. So I'm going to collect all of the common things like the W's and the E's. I'm going to take the P out. It's going to look like this. So I've got gamma P over 2, 2 to the P over 2, and then I've taken out this P, and so I have P to the 1/2 over here. All right, and then 0 to infinity. Inside here, I've collected all the terms, and if you have trouble with this, seeing how I go from the green to the yellow, you should stop and just go ahead and combine these using properties of exponents, okay? Properties of indices. So we've got T squared over P plus 1 divided by 2, and then we've got our W here, right? And then, so that W and this W. So then we're going to take our, then we got our, so this W is, hold on, let me just make it clear that it's in the exponent. So this little W here is in the exponent. And then we've got our other W, which is these ones combined, which is going to look like this, P plus 1 over 2 minus 1, and integrating with respect to W. Now, we're almost finished. There's just a few more things to do here. And the next thing we want to do is basically recognize that we have the kernel of the gamma distribution PDF here. And so what I mean by that is this, the kernel of the gamma PDF, we saw it earlier in the previous video. It's this. Hold on, that's not right. I don't know why I'm writing so fast all of a sudden. So it's x to the gamma minus 1, multiply that to e to the beta x. Okay, so if I just change the order here, you'll be able to see that we do in fact have this form where here our beta, so in this case, we can say our beta would be this negative 1 squared P this. So that would be like our beta, right? And the W would be our X. And then we also have this gamma minus 1, where our gamma would look like this, P plus 1 over 2. Okay, so we do have, in fact, this idea. And actually, I forgot the 1/2, didn't I? And there should also be like a 1/2 here. Although I don't think actually that I need the minus sign. So I'm gonna, well, yeah, I mean, the minus sign would be distributed in there somewhere. Okay, so don't forget about the 1/2 like I did. Okay, so now what it means is that we can replace this integral here as such to get the final product here. Okay, so it's going to look like this. Maybe I'll write it in green. So the probability density function of the t distribution will look like this. We're going to have 1 over the square root of 2 pi multiplied, let me extend this, multiplied by the gamma p over 2, and then we have 2 p divide 2, and then we have the square root of p. And now we're replacing our integral with our gamma. Okay, so I'm going to get gamma of, I'm going to write it like this, actually. I'm going to write it like gamma of p plus 1 over 2 times this 2 over 1 plus t squared over p. And then this is going to be p plus 1 over 2 power. Okay, and you can play around with the algebra to convince yourself that that's exactly true. Okay, so how it ended up from here to here. Okay, so then because I want to make it look a little bit more like what you might see on the Wikipedia page, I'll just say let p equal v. So if you go look at the Wikipedia page after this, you'll see it looks the same, but there's a few things that are slightly different, and that's just the result of algebraic simplification. So here it will look like this. We're going to get gamma of v plus 1 over 2. And then here we've got our 2 over 1 plus t squared divided v. Here we've got v plus 1 over 2. And then this is all dividing the square root 2 pi. So there's a derivation where we can remove the 2, and that will be a v. I mean, not a derivation, but a algebraic manipulation, but I didn't do it here. And so this is the final product. Okay, so this is our this is the probability density function for the t distribution. And in the next video, I will use this function to plot a few graphs, and then I will use the integration of this function to show you how we can calculate some probabilities. Okay, and then in the video after that, so in the next video, we're just going to look at some demonstrations of graphing this thing, graphing this function, and then how exactly are we getting that this t value is corresponding to this probability. So I'll show you how when we integrate the probability density function, we get the cumulative density function, which gives us, oops, I forgot the equal sign, which gives us the probability, right? So we'll be able to look at that. And then after that, the video after that, I will show you the manual. Well, actually in the same video, I'll show you the manual calculation. And then from there, after that, I'll show you the implementation in Python. Okay, so hopefully this is interesting and insightful, and thanks for watching.